some insects are able to walk on the surface of a pond, but you quickly sink to the bottom when you try to walk on water? And why do lakes freeze from the top down in winter? In a word, the answer to all of these questions is polarity. Water is a simple molecule made up of one oxygen atom and two hydrogen atoms, but it is essential to life. In fact, water makes up approximately 60% of the adult human being's body weight. The polarity within those water molecules gives this common substance the properties that make it unique and life-sustaining. Polarity refers to the unequal sharing of electrons within a molecule. For water, the bonding between the oxygen atom and two hydrogen atoms within a single water molecule is like a tug of war between a big, strong football player and a cute little toddler. Oxygen is a larger atom with more protons in its nucleus than hydrogen. These positive charges are like a person's physical strength. They are able to attract the negatively charged electrons in the bond, just like a strong individual is able to overpower a weaker individual in a tug of war. So, oxygen is able to attract more than its fair share of electrons. Because hydrogen is smaller and has less strength, or fewer protons, it loses a tug of war and attracts fewer than its fair share of electrons. So the oxygen in water behaves as though it's negative, and the hydrogens behave as though they're positive. The bonds within a single water molecule are called polar covalent bonds. Covalent means that the electrons are shared. But, as we just learned, polar means that these electrons are not shared equally. In water, the oxygen acts negative, and the hydrogens act positive. Since negative and positive attract, that oxygen is attracted to the hydrogen atoms in neighboring water molecules. A special type of bond forms between water molecules known as a hydrogen bond. Hydrogen bonds don't just happen in water either. They can form between a water molecule and different substances that are polar or ionic. Water's ability to stick to itself is called cohesion, while water's ability to stick to other substances is called adhesion. Now, think back to the initial questions. First, why are some insects able to walk on water? Surface tension due to hydrogen bonding creates a thin film on the surface of water that gives enough resistance for super light insects to walk on. You can't walk on it because the hydrogen bonds aren't strong enough to hold you up. Why does ice float on top of liquid water? For most other substances, the solid state is more dense than the liquid state. But that is not the case for water. Hydrogen bonds keep water molecules farther apart in frozen water than in liquid water. The farther apart the molecules are, the less dense that solid is. So ice is about 9% less dense than water, which means it floats on the top. That's why lakes freeze from the top down and aquatic life is able to survive through a cold winter every year. It is the polarity of the water molecule and the resulting hydrogen bonding that account for water's unique properties. So, the reason that water is so special, from inside your cells to the world's oceans, is simply because it is a polar molecule.
Water. Here we are. This is chapter 3. We're going to have a test on chapters 1, 2, and 3. So 2 is supposed to be review. 3 is not that hard. And so we will take a test as soon as we're done with chapter 3, and that's our first unit. Our next unit will be on chapters 4 and 5. Do this well, because it's going to get harder. But spend time here. Read every word that I ask you to read, please, and do everything I ask you to do. And you should be well on your way to understanding the beauty of water and how it helps with life. Well, we're not going to have you turn in any of these learning targets, these things that you write down. We are going to pause a couple times, and I'm going to have you kind of just pause and go over the concepts that we've just gone over. Today's all about theory. There's really nothing hard to it. And then the next lecture will be a little bit harder with a pH. We'll do some math and stuff like that. I don't like all of this chapter. I think there's some stuff in here that just like the extra orb, the D, the F, and the P orbitals in atoms, there's just too much math at the end when it comes to buffering and pH. I'll let you know what you need to know for the AP exam. Make sure that you answer all the questions in the reading guide. Do the test your understanding at the end of the chapter. There's certainly some concept check questions I want you to complete. And then there's a few of these Mr. Anderson videos I'd like you to look at. But there's no websites for chapter 3. When I look in the book here, right now we'll talk about pages 44 through the left side of page 48. So that's what we're doing. Now, again, this is just a lot of theory as to why water is important. So go ahead and ponder this question for a second. How? How does water allow life to exist on the earth? People argue that it's super important. Organisms die when they don't have water, but what does it do? I have a graphic up here. You can pause this if you need to. Water does a lot of things. It's super important. And we're going to talk about some characteristics of water. But it all comes down to, you probably guessed it, the hydrogen bonding that we learned about with that unequal positive and negative charges, those partial positive and negative dipole charges in the water molecule, and how then water can orient itself with other water molecules. We'll get to that again, we'll review, but that's kind of the basis for all of these concepts that we're about to learn here.
Water is virtually everywhere, from soil moisture and ice caps to the cells inside our own bodies. Depending on factors like location, fat index, age, and sex, the average human is between 55 and 60% water. At birth, human babies are even wetter. Being 75% water, they are swimmingly similar to fish, but their water composition drops to 65% by their first birthday. So what role does water play in our bodies, and how much do we actually need to drink to stay healthy? The H2O in our bodies works to cushion and lubricate joints, regulate temperature, and to nourish the brain and spinal cord. Water isn't only in our blood. An adult's brain and heart are almost 3/4 water. That's roughly equivalent to the amount of moisture in a banana. Lungs are more similar to an apple at 83%, and even seemingly dry human bones are 31% water. If we are essentially made of water and surrounded by water, why do we still need to drink so much? Well, each day we lose 2 to 3 liters through our sweat, urine, and bowel movements, and even just from breathing. While these functions are essential to our survival, we need to compensate for the fluid loss. Maintaining a balanced water level is essential to avoid dehydration or overhydration, both of which can have devastating effects on overall health. At first detection of low water levels, sensory receptors in the brain's hypothalamus signal the release of antidiuretic hormone. When it reaches the kidneys, it creates aquaporins, special channels that enable blood to absorb and retain more water, leading to concentrated dark urine. Increased dehydration can cause notable drops in energy, mood, skin moisture, and blood pressure, as well as signs of cognitive impairment. A dehydrated brain works harder to accomplish the same amount as a normal brain, and it even temporarily shrinks because of its lack of water. Overhydration, or hyponatremia, is usually caused by overconsumption of water in a short amount of time. Athletes are often the victims of overhydration because of complications in regulating water levels in extreme physical conditions. Whereas the dehydrated brain amps up the production of antidiuretic hormone, the overhydrated brain slows or even stops releasing it into the blood. Sodium electrolytes in the body become diluted, causing cells to swell. In severe cases, the kidneys can't keep up with the resulting volumes of dilute urine. Water intoxication then occurs, possibly causing headache, vomiting, and in rare instances, seizures or death. But that's a pretty extreme situation. On a normal day-to-day basis, maintaining a well-hydrated system is easy to manage for those of us fortunate enough to have access to clean drinking water. For a long time, conventional wisdom said that we should drink 8 glasses a day. That estimate has since been fine-tuned. Now the consensus is that the amount of water we need to imbibe depends largely on our weight and environment. The recommended daily intake varies from between 2.5 to 3.7 liters of water for men and about 2 to 2.7 liters for women, a range that is pushed up or down if we are healthy, active, old, or overeating. While water is the healthiest hydrator, other beverages, even those with caffeine like coffee or tea, replenish fluids as well. And water within food makes up about 1/5 of our daily H2O intake. Fruits and vegetables like strawberries, cucumbers, and even broccoli are over 90% water and can supplement liquid intake while providing valuable nutrients and fiber. Drinking well might also have various long-term benefits. Studies have shown that optimal hydration can lower the chance of stroke, help manage diabetes, and potentially reduce the risk of certain types of cancer. No matter what, getting the right amount of liquid makes a world of difference in how you'll feel, think, and function day to day.
Okay, so water is what's important here. Remember this picture. This is a picture of 4 hydrogen bonds, which can be created when water molecules bond to one single central water molecule here. The reason why there's 2, so we probably get that there's going to be 2 water molecules that are orienting themselves. Let me show you up here on the board. So if this is a partial positive charge here and here, I get it that there's 2 that they're gonna bond right there to this central water molecule. But what I tried to say in the last lecture was that there's actually 2 bits of negativity here, and so we can have 2 more water molecules oriented correctly with their hydrogen atoms oriented towards this partially negatively charged oxygen atom in this central water molecule. And you see that up here. I'm sorry I made that more complicated than I definitely needed to. Here are these hydrogen bonds. This is, again, the basis for this whole chapter. Let's pause and let's have you draw this. So go ahead and draw it. You can press pause on the lecture if you like.
Brownian motion of water molecules. Water molecules travel at more than 1,400 miles per hour at room temperature, but they are packed so tightly that they seem to collide and move in a random direction more than once per picosecond. Brownian motion of water molecules. Water molecules travel at more than 1,400 miles per hour at room temperature, but they are packed so tightly that they seem to collide and move in a random direction more than once per picosecond.
So this is important. I want you to think about that little video you just saw. Anytime you see any water, I want you to think of them moving as fast as a bullet. They say like super, super fast. The water molecules are breaking and reforming these hydrogen bonds with their friends that are nearby them. But it's very dynamic. It's not static at all. And as you boil them, they're going to move even more quickly. As you cool them, they're going to move less quickly. But the point is that this is a super active solution here of water molecules. So go ahead and pause for a second and make sure that you get these points down with this learning target here. You don't have to write it. Go ahead and press pause if you need to. I'm going to move on. I think this is interesting because I saw this picture and this is impossible. I know sometimes people at restaurants, they don't want to deal with people ordering water, or maybe here at this whatever restaurant, people ask for water and they don't want to give it to them. But if water's out of stock, then Mug Root Beer and Dr. Pepper, Diet Dr. Pepper are also out of stock, because all that's done in a situation like this is they have a big CO2 cartridge that they turn on, and then they get these bags of syrup that make up kind of the constituency of the drink, and then they just get tap water from town. So if water's out of stock, those other 2 things should be out of stock. Saw that, didn't make any sense. So there's 4 important properties. So here's the first one right here. Go ahead and write down cohesion and adhesion. And these are the important properties for life on this planet. You know, I grew up in Northern California, and there were many redwood trees and sequoias out there if you went to the right places. And I often looked at these trees that were hundreds of feet tall, and I said to myself, how does the water get up there? How does it? There must be water that goes up there. I know now that it needs to go up there for photosynthesis, but how? I mean, for me to pick up a gallon of water and maybe put it over my head, that's 8 pounds, 8.4, 8.7 pounds. A gallon of water and put it over my head. That weighs a lot, and it would take a lot of energy to get tons of water up there to the upper reaches of these trees. So how do plants do it? Well, cohesion and adhesion. Here's the first one, adhesion. Adhesion is the stickiness of something to something else. And I don't mean to be vague there. So I have some tape here. What I mean by this is that this tape will adhere to my shirt. So this is adhesion. This tape is adherent to my shirt. It's the same with water. Water, because of its partial positive and negative charges, it will kind of semi-bond or pseudo-bond real quickly to different things, such as the inside of a xylem, which are these plants, dead plant cell walls called trachea. But the point is that there's some sort of stickiness there. And that's going to allow water as it moves up the trunk of a big tree to kind of stick on there and not fall back down due to gravity. So that's adhesion. Well, but also water can stick to itself, and that's called cohesion. When something is coherent or it's cohesive, it sticks to itself. So we know this through hydrogen bonding, that water can stick to itself. You can see that here also in this picture, that the water molecules up there in the upper right are sticking to themselves. And this will also help water not fall back down towards the earth as it's being brought up the trunk. And I'll tell you later how it's being brought up the trunk. But the point is sticks to itself. And then there's a solid column of water in like a tree like this. In fact, guys, have you ever wondered why if you went to, let's say, Walmart, you did something wrong, your girl's mad at you, you pull up some flowers out of Walmart, you stick them in the backseat of your car, you do your thing for a few hours, you go home, you shove them in water, you think you've done a great job, you hand them to your girl the next day, and within 2 days they're dead. And the reason why is because there was a solid column of water going up the stem of the rose, and your mom will tell you that you need to cut the stem and then put it back in water. And the hope is that as the water continues to get up to the leaves so they can do photosynthesis, the rose doesn't know that it's in the back seat of your car. It still has water and light and it's still living. You want to cut above that solid column of water so that it can restart to suck more water once you stick it in a vase. So make sure that you cut the rose high enough and do it at an angle you get more of a surface area for suction of water. Water striders use this to their advantage, this cohesive property of water. And there are many organisms that do. You can see here that because of the hydrogen bonding, they can kind of float on top of water.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, maybe run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard?
Okay, so I've seen those guys in Costa Rica, and they're really neat. So that's cohesion is also not only going to help plants, but it helps water striders and these basilisk lizards. We have to worry about it when diving. There's a lot of kind of hydrogen bonding of the water molecules on the surface of the water, and often a jet spray of water. This coming summer will be the Olympics. Look for that in the 10-meter platform diving. The idea is not only does it give it a target for the diver, but number two, kind of breaks up that surface tension due to all the cohesion there. However, this can be a problem. I had a friend, Carrie Garbarolio, who she fell off of a bridge where we lived out in Northern California. It was a high bridge, and she hit the water like flat on her back, and apparently it's like as hard as cement, and she had to go to the ICU and her kidneys were failing. I remember it was just a really scary situation. Let me show you a similar situation that happened in Washington State.
Many of us have already seen this gut-wrenching video shot last week that's gone viral. It shows 16-year-old Jordan Holgerson getting shoved off a roughly 60-foot bridge at Molten Falls. She broke 5 ribs, punctured both lungs, and is bruised head to toe. She could have died.
Wow, so cohesion is really, really strong. Let me show you someone else who's using cohesion to their advantage. Professor Splash.
Please do not try this at home. All right, ladies and gentlemen, because of the dangerous act that we have before us, we're going to need as much silence as possible. Needs to focus. Professor Splash about to risk his life. Complete silence, please. Why are we doing this?
Hey, Professor Splash, please do never wear a swimsuit that looks like that, please. Let me show you one more thing that is an example of cohesion and hydrogen bonding. It's pretty neat. It's pretty cool, huh? So the next time you ever see a drop of water go into, say, a cup of water or anything like that, think about this, how it's bouncing due to the surface tension because of hydrogen bonding. It's pretty sick. So certainly that's on the Google Classroom, and you can watch that as many times as you want. Saturday night's coming up. G-rated. It'll be fun to do with your friends. So go ahead and take a pause and go ahead and tell someone about these things. Define cohesion and adhesion, and then explain why they're important, please. Well, I said that there were 4 properties of water that are important to living things, but we're only going to go over 3 today. This next one is moderation of temperature, and here's a question I have. If you look at this map of Southern California in the summertime, you can see that it's much cooler on the coast than inland. Why is that? Well, water can absorb or release a large amount of heat with only a slight change in its own temperature. Where? Where does water absorb this heat? So I'm holding a beaker of water here, and if I wanted to boil this and I could put a flame underneath it, it would take a long time for this thing to boil. All that heat is going into this system, and where is it going? Because we don't see a very big reaction. You can put a flame underneath this for a minute or 2 and then still stick your finger inside of it. And all that heat, but you couldn't stick your finger over the flame. All that heat is going somewhere, but the temperature is really not changing that quickly in the water. Where's it going? Where do you think? I mean, what has been the theme here? In the hydrogen bonds. So the idea is that hydrogen bonds will accept that heat, they'll start to vibrate some more, and so on, and they will continue to vibrate, hold these water molecules next to one another. Although they'll start to move more quickly, they'll still create and break those hydrogen bonds again and again until those literally break for the last time. And when that happens, water molecules can actually leave the system as steam. And that's why people say if you get burned by steam, it's so much hotter than the 212 degrees Fahrenheit or 100 degrees Celsius that the water actually is because there's so much energy that's being held there, that's being released. Sometimes steam is like 1,000 degrees or something like that because there's tons of heat there that is released as a result of these hydrogen bonds breaking for the final time. Likewise, I've written up here evaporative cooling. The whole idea is that you can go out and you can run around the track. You're made up of 70% water, and you're doing all this cellular respiration. It's totally inefficient, the breakdown of food in the presence of oxygen in your mitochondria to make ATP, to contract your muscles, to run around the track. It's totally inefficient. You're creating tons of heat, but your temperature really doesn't change, maybe just by a degree or two. It's the same thing here, is that your body is resisting temperature change because it's holding all that heat in these bonds. Now, one way that you can get rid of some of this heat is through sweating. So if your sweat pores open up and water is released on the surface of your skin, it will then take a lot of that heat that's in those hydrogen bonds between the water molecules and release them out to the environment.
So another famous science guy named Robert Krulwich talked to me and said he was going to be sending me an article about sweating. It was kind of weird because I didn't really feel like I needed to read an article at that moment because I happened to be talking to him in my car, so I was already sweating my brains out. Now, I never really appreciated sweating that much because it makes my shirt all soggy and my hair all wet and nappy, and I start to worry that I smell bad, but I was curious to know more about it. The article was about the experiments that this guy named Charles Blackman did about sweating. It was actually kind of hard to read because it was written 200 years ago, so the words were all spelled like this, and so it took me a little while to get through it. Anyway, Charles Blackman's experiment went like this. He put proper English gentlemen into a not very proper English setting. One at a time, he put them into a small room with a dog, a raw beef steak, a few eggs, and an iron stove fired up until the room temperature reached 210 degrees Fahrenheit. After a few minutes, the men began to sweat, and the dog began to pant. Understandably, some of the men began to remove their clothes, and as they took turns going into the room, one would say to the other, "I say, old boy, I would recommend you remove your trousers in there." "Thank you, kind sir. Jolly good idea. It does seem a trifle stuffy, doesn't it?" And so on. Now, water would boil at 212 degrees, but even at 210, the men showed no pain. Blackman was curious to know how much more they could stand, and so he continued to heat up the room to 220 degrees, then 240. The men were curious too, although perhaps a little less enthusiastic about it. At 260 degrees, the men were drenched in sweat, but were still able to stay in the room for 7 to 10 minutes at a stretch with what they called tolerable ease. Although they had not quite figured it out yet, it was the sweating that kept them safe. The thin layer of moisture on their bodies was enough to keep them from burning up. Today, we call this process evaporative cooling. However, two of their companions, the steak and eggs, which could not sweat, had been roasted hard and dry. Blackman did not report that the steak and eggs smelled like, and there's probably a very good reason for this. The star of the show was the dog, who showed no other sign of uneasiness other than panting and holding out his tongue, and was able to stay in the room for 30 minutes at a time at 236 degrees. The dog kept cool through his panting and was perfectly lively and fresh as a daisy after leaving the room and getting into the cool air. Sweating is yet another thing that separates us from many other popular protein-based life forms. So now I'm perfectly happy to sweat, and you should be too.
Sweet. Okay, so last thing. Insulation of bodies of water by ice. What that means is that ice is going to insulate bodies of water and allow organisms, think of Nottingham Lake, in the middle of the winter, allow them to survive under there. There's fish that live under there, even though sometimes it's minus 10, minus 15 degrees outside. There's liquid water under there because it's insulated from the external environment by the ice. So water is weird how as a solid it's less dense than as a liquid. I think it's the only thing that science has ever found to be that. And So let's go through this, but let's start with a video. Yes, that's pretty cool. So this all has to deal with density. So remember from chemistry that density is mass over volume. So if we have a mass of water, let's say we have 1 kilogram of water, we can weigh it on a scale in the presence of gravity, that's mass. Let's say we have that, but there can be different instances where that 1 kilogram of water's volume could change. The water molecules might start to move a little bit more slowly, and I'm going to show you that there's an effect due to that, and it causes it to become more dense. And you can see that here with this beverage that has been left in the freezer. The mass didn't change, but the volume changed of the liquid that was in that bottle. So here it is, insulation of bodies of water by floating ice. You can see this krill here, it's underneath this ice and it's being kept safe. You can see here that with liquid water, the water molecules are always moving and hydrogen bonds are breaking and reforming. And what happens with water is when it turns to ice, everything slows down. The distance between all these hydrogenly bound water molecules kind of gets as great as they can possibly get. And so it spreads out that 1 kilogram of water, or whatever the mass is of the water. You can see it's a lot more organized. This is called a lattice here. And then as a result, ice floats. And we know that ice floats when it's in liquid water. And so ice is less dense than liquid water. It floats, allows things to survive. I had a movie here. Okay, movie's not working. Thanks, everybody. Good luck with the beginning of chapter 3.